Good day and welcome to my YouTube channel. I am Archie Francis. Please don't forget to subscribe and press the like button. So today we're going to be taking on fundamental or basic unit and derived unit. So the fundamental unit are essential units. We use them in the combination of them to get any derived unit we want. Units such as mass in kilogram, time in second, length in meters, we even have current in amperes, and so on. So with our application of this fundamental unit, we'll be able to get any unit whatsoever we're dealing with. So this is a preliminary step in physics, which help us with the basic things we need to know and how to go about the various units in terms when we go a little deeper in terms of motion and other stuffs in physics. So let us start with the fundamental unit here. So we're talking about the fundamental units, so derived unit. So we're going to use the fundamental unit to form our derived unit, which is basic. So let's start from the lowest variable we can begin with. Let's say velocity, for example. This is velocity. Velocity is defined as distance over time, or some tests will say displacement over time. So let's use distance. Distance over time. Now, in this distance, the unit for distance is meters. So we have our m, and time is in seconds. So this can definitely become, if I take the seconds up, I now have meter per second. So it's either this or this. So by this, we're able to derive the unit. Velocity was able to be achieved through the fundamental unit, which is meter and time. That is how we get there. So having known how to do this, we also have what we call dimension. So we're going to apply the dimension alongside that. When we are done deriving the unit, we use the dimension to finalize. So in dimension, let's look at this basic unit. We have time, which is in seconds, but the word time, let me put it here, time. We have distance or mass, which is in kilogram. We have length, which is in meter. So for the dimension, how do we know the dimension for this? Wherever we see time, which is supposedly going to be in seconds, we use the capital T to represent this for time. So wherever you see capital T, that is for our time. Capital M for mass and capital L for meters. So meters will be used, the dimension for meter will be capital L, the dimension for mass will be capital M, and so on and so forth. That's how we go. So if that is true, we come down here. Let's put this one in its dimensional pattern. This is what? This is our meters, which is length. Alright? So we put our capital L, time in seconds. Time in seconds. So we use capital T. So we put our -1. This becomes the dimension for velocity. So that is the trend, and that is how we're going to go about it. So do not forget, when we get there, we'll see how we roll on. So let's take another variable. Let's call it acceleration. Acceleration is change in velocity over time. So this is equals to change in velocity over time. And we know that velocity is distance over time. Distance over time divided by time, which is down. Divide by time. So this becomes the unit for distance. Let's use our meter over time is in seconds. divide by time in seconds. This is over 1. So fraction will have us know that when we have division here, we change it to multiplication, we have 1 up and s will come down. So this will now give us meter over second squared, s times this second squared, which is the same thing as meter x minus 2. And the dimension, now this is for meter, which is length, this is time, which is t, and minus 2. So this becomes the dimension, and this becomes the derived unit. So when they ask what is the derived unit, or what is the unit for acceleration, you should derive it to show us the unit for acceleration. This is what you must do to get your acceleration. And this is the dimension therein. Let's take another question. Let's take force. Force is mass times acceleration. Now, mass is direct. Let's call it in kg. Acceleration now is change in velocity over time. I come over here, this is my kg for mass. Velocity alone here is distance over time. That's for velocity over time, divided by this other time. So I come over, I have my kg for mass, my distance is in meter, my time is in second, divided by time again in second over 1. So this is my kg, this is time, sorry. My kg times meter over second times 1 over seconds. And this is equals to kg meter over second squared. Let's come over here. Now, I have my kg meter over second squared. Now, what is, if I want to put it the other way, I can still have it as kg meter second squared. This way, they are both correct. So the dimension, we have mass. This is kg, the capital for the dimension become capital N. Mass. This is meter is in length. This is second is t minus 2. This becomes the dimension for force. So this is how we go. But then we'll continue to solve more and see what we are doing about it. So that is it. Let's take let's take another question. Let's take density. Density is equal to mass over volume. And mass here, volume is length is in meter times the breadth is in meter times the height is in meter. So I can rightfully say mass is in kg over m times m is m cubed. This is kg m minus 3. This is the derived unit for density. Now what is the dimension? Kilogram is mass, capital M. This is meter for length. And this is minus 3. This becomes the dimension for density. So through this trend, we'll continue to move on and on to solve a whole lot of variables. We're going to look into them, all of them, and see the best we can get out of them. So let's take another variable. Let's take pressure. This is pressure, which is force over area. Now, what is force? Force is mass times acceleration. This is for force. Area is length times breadth. Length is in meter times the breadth is in meter. So I will continue. Let's go on. Mass is in kg times acceleration is change in velocity over time. Divide by, this is all of this divided by meter squared. So divide by m squared. So this is equals to my kg, kg times velocity is distance. Distance is in meter over time. Time is in seconds. Let me put it seconds. This is for velocity. Now divide by second, which is time again. Now also divide by m squared, which is this. Let's cross over to the side. Now my kg times n over x, which is this. This is over 1. So I'll change this to times 1 over x here. This goes up, this comes down. Times, when I change this to times 2, this becomes 1 over m squared. So kg, which is for mass, times, okay, let me just proceed. Kg times, this is my n, that's all. I come over here, I have s squared, s times x, and m squared. So, let's proceed. Now, this becomes kgm. If I want to take out one of these, so if I cancel this, I cancel this, I will now have kg up only. Okay, let me leave it like at that. Now I have over s squared n. So if I want to take them all up, I now have kg n minus 1 x minus 2. Therefore, the dimension kg is in mass, meter, that is length, minus 1, time is minus 2. This becomes what? The dimension for pressure. Now, let us take another variable. Let's take work or energy. Energy is the ability to do work. Now, what is work? Work is force times distance. Force times distance. That is for work or energy. So, what is force? Force is mass times acceleration. Now times distance. This is my mass times acceleration is change in velocity over time times distance. And this is my mass times velocity is distance over time. This is velocity, distance over time, divide by time. Time, distance. Now, let's break it down. Mass is in kilogram, times distance is in meter, time is in seconds, divide by time again, which is in seconds, time distance in meter. Okay, now this becomes my kg meter over seconds, which is this, times 1/seconds times meter. So this is kg meter square over x square, which is the same thing as kg meter square x minus 2. Now, what would be the dimension for this? The dimension is kg is capital M, meter is length, capital L raised to the power 2, time, capital T minus 2. So this becomes the dimension for energy or the dimension for work. So all of them are the same. If energy is the ability to do work, so work is force times distance, which means the two of them can be used. So we're talking about the energy, we're talking about the work done. So let's take power. So power is what we're going to be dealing with right now. Power is the energy expended over time. So we say energy over time. And we said earlier that energy is work. And work is force times distance. So this is force times distance over time. And force is mass times acceleration times distance over time. So we come over here, now we say this is mass times acceleration is velocity over time times distance divided by this time here. Okay, let's take this other side. Try to manage it. And now my mass, this is mass times velocity is distance over time. Velocity is distance over time for velocity. Divide by time times distance, which is this, divide by time. Okay, let's break them down. Mass is in kilogram, distance is in meter over second, divide by second times distance in meter, divide by seconds. So this is my kg times meter over second. This is over 1 times 1 over second times meter times 1 over second. So this is my kg meter squared m times n over second cube. Second raised to the power 3. So which is the same thing as kg meter squared x minus 3. And the dimension now becomes kg is capital M, meter is L raised to the power 2, and time is minus 3. So that is that for power. Moment. So let's take another moment. Is force times distance. So moment is force times distance. If you've dealt with equilibrium before, they say the moment of a force about a point is the product of the force times the perpendicular distance from the point to the line of action of the force. So it's force times distance. What is force? Force is mass times acceleration times distance. And mass, okay, let's write it. Acceleration is velocity over time times distance. And this is equal to, this is my mass. Velocity is distance or displacement over time divided by time times distance. And this is equal to mass times distance is in, okay. Let me just take them out at once. Mass is in kg times distance in meter over time in second divided by time in second over 1 times distance in meter. So this is the same thing as kg times meter over seconds times 1 over second times meter. So if I come over here, I will be having, this is kg meter square over second square, which is the same thing as kg meter square second minus raised to the power minus 2. So the dimension now becomes kg is capital M, length for meter raised to the power 2, and time is minus 2. So this becomes the dimension for moment. Oh, let's take momentum. Is mass times velocity, the product of its mass and its velocity. Momentum is mass times velocity. Let's take momentum. Mass times velocity. So if momentum is the product of its mass times velocity, I think that one is going to be shorter because we know mass is direct kg, velocity we just move over to do our distance over time, and that's all. So we rationalize it. So this is mass times velocity is distance or displacement over time. So this is, mass is in kg, time distance is in meter, over time is in second, which means kg meter per second. So, and the dimension therefore becomes kg is capital M, meter is capital L, time is capital T minus 1. So this becomes the dimension for momentum. So let's look at another one. Okay, impulse, good. So we look at impulse. Which is force times time. So if impulse is force times time, I think, okay, just take a look. What is force? Force is mass times acceleration times time. And this is my mass. The acceleration is velocity over time times time, and this is my mass, and velocity is distance over time, as for velocity, divided by time times time. Okay, let's break them down. This is mass is in kg, and distance in meter over time in seconds, divide by time in second over 1 times time. So let's say kg times meter over second, which is time, times 1 over second times second. So this gives me kg meter second over second squared. So this can be cancelled. This will go with this. So I now have kg meter over second, which is the same thing as kg meter x minus 1. Okay, so if I want to put this in the dimension becomes kg is capital M, meter is L, and this is second, t time minus 1. So that becomes my impulse. Is there anyone who've not talked about pressure, or talked about, technically we've talked about everything. So, but all things being equal, there could be other variables which I have not gone to. But what we have done today is to show you how important the fundamental units are in terms of using them to get our derived unit, using them to get our dimensions, and even to solve equations if we want to go as far as that. And for you to be able to have a full grasp over what I am just doing right here, you must first of all know the definitions of these particular variables which I've used, like saying acceleration is change in velocity over time, and you know what is velocity as distance over time. You know what is pressure is force over area. Force is what? Mass times acceleration. You'll be able to break it down to that level. Power is energy expended over time, when energy is the same thing as work, and work is force times distance. And you look at force to be mass times acceleration. When you're able to put all these things in the right place, in the right proportion, you realize that everything will be within your grasp. You would find them difficult to deal with. So it is important before you get into solving the derived unit, which you are likely going to get into. But you first of all have to know the definition of those particular variables which you're going to deal with, and how to transform the fundamental unit into derived unit by changing them from their time, which is in seconds. If you want to turn it to dimension, the time, which is second, become capital T, and so the meter become capital L, and so on and so forth. So with that, I say you all have a wonderful time. See you again when I see you.